Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Deep beneath our feet, Earth's surface moves with relentless determination. While we go about our daily lives, massive chunks of the planet's crust drift across the molten interior like slow-motion bumper cars, colliding, separating, and reshaping the very ground we stand on. But here's a question that might keep you awake at night. Could we actually witness the birth of an entirely new continent within our own lifetime? The idea seems impossible at first glance. Continents are ancient, stable features that have existed for millions of years. North America, Europe, Asia, these massive landmasses appear permanent, unchanging monuments to geological time. We're taught that continental drift occurs over millions of years, that the processes shaping our planet operate on timescales so vast they're almost incomprehensible to human minds. Yet something remarkable is happening right now in the North Atlantic. Iceland, that rugged island nation known for its geysers and northern lights, is literally growing before our eyes. Every year the island expands by approximately 2 centimeters as new volcanic rock emerges from the depths. In geological terms, this is breakneck speed, like watching continental formation in fast forward. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe, it's free, and it helps us grow this community together. This rapid expansion raises fascinating questions about the nature of continental formation. If Iceland can grow this quickly, what about other locations around the globe? Are there hotspots of geological activity where new land masses might emerge, within decades rather than millennia? The answer lies in understanding the fundamental forces that shape our planet. Earth's interior is a churning mass of molten rock, driven by radioactive decay and primordial heat left over from the planet's formation 4.6 billion years ago. This internal engine powers the movement of tectonic plates, the massive sections of crust that float on the semi-liquid mantle below. Most continental formation occurs at specific types of geological boundaries: divergent boundaries, where plates pull apart, create new oceanic crust and sometimes new landmasses; convergent boundaries, where plates collide, can thrust land upward into mountain ranges; transform boundaries, where plates slide past each other, generally don't create new land but can dramatically reshape existing coastlines. But there's a third mechanism that operates independently of plate boundaries: volcanic hotspots. These are columns of superheated rock that rise from deep within the mantle, punching through the crust above like geological blowtorches. Hawaii, Iceland, and Yellowstone all sit atop such hotspots, and they represent some of the most geologically active locations on Earth. The key insight is that not all geological processes operate on the same timescale. While the gradual drift of continents occurs over millions of years, volcanic activity can create substantial new land in mere decades. The island of Surtsey, off the coast of Iceland, emerged from the ocean in 1963 and grew to over 1 square mile before volcanic activity ceased 4 years later. This rapid land formation suggests that under the right conditions, significant new land masses could indeed appear within a human lifetime. The question isn't whether it's geologically possible. We know it is. The question is where it might happen next, and whether the resulting landmass would qualify as a genuine continent rather than just another island. To answer this question, we need to examine the current state of our planet's geological activity. We need to identify the locations where Earth's internal forces are most actively reshaping the surface, and calculate whether any of these processes could produce continental-scale results within the next 50 to 100 years. Understanding how continents form requires diving deep into the fundamental mechanics of our planet's geology. Earth's surface isn't a solid, unchanging shell. It's a dynamic puzzle of moving pieces, each responding to the immense forces generated by our planet's molten interior. The story begins nearly 3,000 miles beneath our feet, at the boundary between Earth's core and mantle. Here temperatures exceed 4,000 degrees Celsius, hot enough to melt most rocks completely. This extreme heat creates convection currents in the mantle, similar to the rolling motion you see in a pot of boiling water, but operating on a planetary scale and over millions of years. These convection currents drive the movement of tectonic plates, the massive sections of Earth's crust that carry our continents and ocean basins. There are 7 major plates and numerous smaller ones, all in constant motion at rates typically measured in centimeters per year. While this seems slow, the accumulated movement over geological time is staggering, enough to open and close entire ocean basins. Continental formation occurs through several distinct mechanisms, each operating under different conditions. The most common process involves volcanic activity at mid-ocean ridges, underwater mountain ranges, where tectonic plates diverge. As plates pull apart, molten rock called magma rises from the mantle to fill the gap, solidifying into new oceanic crust. This process creates approximately 20 square kilometers of new seafloor every year. Most of this new crust remains underwater, but under specific conditions, it can rise above sea level to form islands or even larger landmasses. The key factors include the rate of volcanic activity, the composition of the magma, and the underlying geological structure. When these elements align properly, the result can be rapid land formation that's visible within human timescales. Iceland provides the perfect example of this process in action. The island sits directly on the mid-Atlantic ridge, where the North American and Eurasian plates are pulling apart at a rate of approximately 2 centimeters per year. But Iceland isn't just benefiting from normal seafloor spreading. It also sits atop a mantle plume, a column of abnormally hot rock rising from deep within the Earth. This combination of plate divergence and hotspot activity creates ideal conditions for rapid land formation. The mantle plume provides an extra source of molten rock, while the diverging plates create space for this material to reach the surface. The result is an island that's not only growing, but doing so at a rate that's remarkable by geological standards. Volcanic hotspots represent another crucial mechanism for continental formation. These geological features operate independently of plate boundaries, powered by plumes of hot rock that rise from the deep mantle. As tectonic plates move over these stationary hotspots, they create chains of volcanic islands, with the youngest and most active volcanoes positioned directly above the plume. The Hawaiian island chain demonstrates this process beautifully. The Big Island, Hawaii, sits directly over the hotspot and features some of the most active volcanoes on Earth. As you move northwest along the chain, the islands become progressively older and more eroded, showing the path of the Pacific Plate as it moved over the stationary hotspot over millions of years. But hotspots can do more than create island chains. Under the right conditions, they can produce massive volcanic provinces that reshape entire regions. The Deccan traps in India, the Siberian traps in Russia, and the Columbia River basalts in the Pacific Northwest all formed when hotspots generated enormous volumes of lava over relatively short geological periods. The composition of volcanic rock also plays a crucial role in continental formation. Oceanic crust typically consists of basalt, a dense dark rock that forms from relatively fluid lava. Continental crust, in contrast, contains more silica-rich rocks like granite, which are less dense and more likely to remain elevated above sea level. This difference in rock composition helps explain why some volcanic regions remain underwater, while others form substantial landmasses. Areas that produce more evolved, silica-rich magmas are more likely to create permanent continental crust that won't be subducted back into the mantle. Modern technology allows us to monitor these processes with unprecedented precision. Satellite measurements can detect ground movement as small as millimeters per year, while seismic networks reveal the underground movement of magma long before it reaches the surface. This real-time monitoring capability means we can potentially predict where and when significant new land formation might occur. Iceland stands as Earth's most accessible laboratory for studying rapid continental formation. This North Atlantic island nation occupies a unique position on our planet, sitting directly atop the mid-Atlantic ridge, while simultaneously being fed by one of the most powerful volcanic hotspots on Earth. The result is a landmass that's literally growing before our eyes, offering scientists an unprecedented opportunity to study continental formation processes in real time. The islands Position makes it a geological anomaly. Most mid-ocean ridges lie thousands of meters beneath the ocean surface, hidden from direct observation. Iceland's elevation above sea level results from the Iceland hotspot, a column of superheated rock rising from deep within the mantle. This hotspot has been active for at least 60 million years, first creating the volcanic plateau that would eventually become the Faroe Islands before moving to its current position beneath Iceland. The numbers tell a remarkable story. Iceland grows by approximately 2 centimeters per year along its east-west axis, as the North American and Eurasian plates pull apart. This might seem insignificant, but over human timescales, it's substantial. In a single lifetime of 70 years, Iceland expands by nearly 1.4 meters. Over the past 1,000 years, the island has grown by approximately 20 meters in width, but the expansion isn't uniform. The growth occurs primarily along the active volcanic zones that run through the island's interior. The Reykjanes Ridge extends from the mid-Atlantic ridge onto land in southwestern Iceland, while the northern volcanic zone cuts through the island's northern regions. Between these zones lies the western volcanic zone, creating a complex pattern of rifting and volcanic activity. Recent volcanic events demonstrate just how rapidly new land can form. The 2021 eruption on the Reykjanes Peninsula created entirely new lava fields covering several square kilometers. The Fagradalsfjall volcano, dormant for nearly 800 years, suddenly came to life, producing spectacular lava fountains and flows that added measurable new land to Iceland's surface. Even more dramatic was the birth of Surtsey Island between 1963 and 1967. This volcanic island emerged from the ocean floor 32 kilometers southwest of Iceland, growing from nothing to over 2 square kilometers in just 4 years. The eruption began underwater, with explosive interactions between lava and seawater, creating towering steam clouds visible from the mainland. As the volcanic pile grew taller, it eventually broke the ocean surface, creating a new island that scientists could study from its very first moments. Surtsey's formation provided invaluable insights into the processes that create new land. The initial explosive phase, caused by seawater contacting molten lava, created easily eroded volcanic ash and cinder. Only when the volcanic vent rose high enough above sea level to prevent significant water infiltration did more durable lava flows begin forming, creating the stable foundation necessary for permanent land. The island's subsequent evolution has been equally instructive. Erosion immediately began attacking the new landmass, with winter storms carving dramatic cliffs and reducing the island's size. However, continued volcanic activity during the eruption's later phases added more resistant lava flows, helping preserve much of the new land. Today, Surtsey covers approximately 1.4 square kilometers, smaller than its maximum size during the eruption, but still substantial enough to support vegetation and wildlife. Iceland's volcanic activity isn't limited to creating new land. It's also reshaping existing terrain at remarkable rates. The island experiences volcanic eruptions every few years on average, with major eruptions capable of altering the landscape dramatically. The 2010 eruption of Eyjafjallajökull, famous for disrupting European air travel, added new material to the glacier-covered volcano and changed local drainage patterns. Modern monitoring technology reveals the constant geological activity beneath Iceland. The Icelandic Met Office operates a comprehensive network of seismic stations, GPS receivers, and ground deformation monitors that track the island's growth in real time. These instruments detect not only major eruptions, but also the subtle ground movements that precede volcanic activity. GPS measurements show that some parts of Iceland are rising vertically, as well as expanding horizontally. This uplift results from multiple factors: the continuous addition of new volcanic material, the isostatic rebound following ice age glaciation, and the buoyant effects of the underlying hotspot. Some areas are rising at rates of several millimeters per year, fast enough to be noticeable over decades. The implications extend beyond Iceland itself. The island serves as a natural laboratory for understanding how continental crust forms and evolves. The processes occurring in Iceland today are similar to those that created much of the world's continental crust billions of years ago when hotspot activity was more common and intense. Research conducted in Iceland has revealed crucial details about how oceanic crust transitions to continental crust. As volcanic activity continues over millions of years, the repeated addition of lava flows and the chemical evolution of magmas gradually creates rock compositions more similar to continental crust than typical oceanic basalt. This process, observed in real time in Iceland, helps explain how Earth's earliest continents may have formed. Volcanic hotspots represent some of the most dynamic and rapidly changing features on Earth's surface. These geological powerhouses operate like massive blowtorches rising from the planet's deep interior, capable of creating substantial new landmasses in remarkably short periods. Understanding hotspots is crucial to answering whether Earth could grow a new continent within our lifetime, because they represent the fastest mechanism for large-scale land formation our planet possesses. The concept of hotspots revolutionized geological thinking when first proposed in the 1960s. Unlike most volcanic activity, which occurs at plate boundaries, hotspots are fixed columns of superheated rock that rise from deep within the mantle, possibly from the boundary. With Earth's core nearly 3,000 kilometers below the surface, as tectonic plates move over these stationary plumes, they create distinctive chains of volcanoes, with the most recent activity always positioned directly above the hotspot. Hawaii provides the classic example of hotspot volcanism in action. The Hawaiian island chain stretches across more than 2,400 kilometers of Pacific Ocean, but all this volcanic activity stems from a single hotspot currently positioned beneath the Big Island. As the Pacific Plate moves northwest at approximately 7 to 9 centimeters per year, it carries older volcanoes away from the hotspot, allowing new ones to form in their place. The rate of land formation in Hawaii is staggering by geological standards. Kilauea volcano, one of the most active volcanoes on Earth, has been erupting almost continuously since 1983. During particularly active periods, it can produce enough lava to pave a 2-lane highway stretching from New York to Los Angeles every single day. The 1990 Kalapana eruption alone added over 200 hectares of new land to Hawaii's coastline. Mauna Loa, Hawaii's largest volcano, demonstrates the immense scale of hotspot-driven land formation. This massive shield volcano rises over 4,000 meters above sea level and extends another 5,000 meters below sea level to the ocean floor. Its total volume exceeds 75,000 cubic kilometers, making it one of the largest volcanoes on Earth. Remarkably, geologists estimate that Mauna Loa formed in less than 1 million years, extremely rapid by geological standards. But Hawaii represents just one type of hotspot activity. The Yellowstone hotspot, currently positioned beneath Wyoming, operates on an even more dramatic scale. This hotspot has produced 3 catastrophic super-eruptions over the past 2.1 million years, each releasing more than 1,000 cubic kilometers of volcanic material. The most recent super-eruption, which occurred 640,000 years ago, ejected enough material to bury the entire state of Texas under several feet of volcanic debris. Between these massive eruptions, the Yellowstone hotspot continues to reshape the landscape through more moderate volcanic activity and hydrothermal processes. The famous geysers, hot springs, and fumaroles that make Yellowstone National Park unique all result from heat generated by the underlying hotspot. Ground deformation measurements show that parts of the Yellowstone caldera rise and fall by several centimeters per year as underground magma chambers expand and contract. The track of the Yellowstone hotspot across the western United States reveals the potential for rapid landscape transformation. As the North American plate moved southwest over the stationary hotspot during the past 17 million years, it created the Snake River Plain, a distinctive arc of volcanic terrain stretching across southern Idaho. This plain represents one of the most dramatic examples of how hotspots can completely reshape regional geography. Hotspots don't always create island chains or volcanic plateaus. Sometimes they produce even more dramatic results. The Siberian traps, formed around 250 million years ago, represent one of the largest volcanic provinces in Earth's history. This hotspot eruption covered an area larger than the continental United States, with basaltic lava flows up to several kilometers thick. The eruption lasted for approximately 2 million years and likely contributed to the Permian-Triassic extinction event, the most severe mass extinction in Earth's history. Modern technology allows scientists to identify active hotspots that might produce significant new land formation. The Galapagos hotspot, currently positioned beneath the western Galapagos Islands, continues to create new volcanic islands while moving older ones away from the center of activity. Fernandina Island, the youngest and most western of the Galapagos, experiences frequent eruptions that regularly add new land to its coastline. The Afar hotspot in East Africa presents perhaps the most exciting opportunity for witnessing continental formation within human timescales. This hotspot sits at the junction of 3 tectonic plates and drives the rifting process that's slowly tearing the African continent apart. The hotspot's activity has created the Afar Depression, a region where new oceanic crust is forming on dry land, offering scientists a unique window into the earliest stages of ocean basin formation. Recent research has identified several other hotspots that show potential for rapid land formation. The Azores hotspot in the North Atlantic, the Canary Islands hotspot off the coast of Africa, and the Réunion hotspot in the Indian Ocean all show signs of ongoing volcanic activity capable of creating substantial new landmasses. The key insight from studying hotspots is that they operate on multiple timescales simultaneously. While the overall process of hotspot evolution occurs over millions of years, individual eruptions can create significant new land in months or years. A major hotspot eruption in the right location, particularly in shallow ocean areas, could potentially create new landmasses large enough to be considered continental fragments within a human lifetime. Across Earth's surface today, several locations show clear signs of active continental formation processes. These modern laboratories of geological change offer our best opportunities to witness significant new land formation within human timescales. By examining current rates of activity and understanding the underlying mechanisms, we can identify where Earth might indeed grow new continental fragments in the coming decades. The East African Rift System stands as the most promising candidate for witnessing continental birth in our lifetime. This massive geological feature stretches over 3,000 kilometers from the Red Sea to Mozambique, representing one of the most active continental rifting zones on Earth. The rift system is literally tearing the African continent apart, and in the process, it's creating conditions that could lead to the formation of entirely new continental fragments. The rift operates through a combination of tectonic forces and hotspot activity. The African continent sits above several mantle plumes that generate substantial volcanic activity throughout the region. Combined with the extensional forces pulling the continent apart, these hotspots create ideal conditions for rapid geological change. GPS measurements show that the eastern and western sides of the rift are separating at rates of 6 to 7 millimeters per year, remarkably fast for continental processes. The most active portion of the East African Rift lies in the Afar Depression, where Ethiopia, Eritrea, and Djibouti meet. This region sits at the triple junction of 3 tectonic plates, the African, Arabian, and Somali plates. The combination of plate motions and intense hotspot activity has created a landscape unlike anywhere else on Earth, with active volcanism, extensive faulting, and ongoing crustal formation. What makes the Afar Depression particularly significant is that it represents oceanic spreading occurring on dry land. The process creating new oceanic crust along mid-ocean ridges is happening here above sea level, allowing scientists to study continental breakup in unprecedented detail. The Erta Ale volcanic range, a chain of active shield volcanoes, demonstrates the type of volcanism that typically occurs underwater along mid-ocean ridges. Recent events in the Afar region have dramatically illustrated the potential for rapid change. In 2005, a massive rifting event created a 60-kilometer-long crack in the Ethiopian desert in just a few weeks. The Dabahu fissure eruption involved the intrusion of a 2.5 cubic kilometer dike of magma, causing the ground surface to drop by several meters over a wide area. This single event demonstrated that continental rifting can occur in sudden dramatic episodes rather than gradual, imperceptible changes. The Red Sea represents a more advanced stage of the same process occurring in the East African Rift. Over the past 30 million years, rifting has progressed to the point where true oceanic crust now separates the Arabian Peninsula from Africa. The Red Sea is expanding at approximately 1 to 2 centimeters per year, with new oceanic crust forming along the central spreading axis. Importantly, the Red Sea expansion isn't creating just underwater terrain. Several volcanic islands have emerged from the spreading center, with some showing rapid growth rates. Jebel Altair Island experienced a significant eruption in 2007 that added substantial new land to its surface. These islands represent potential nuclei for larger landmasses if volcanic activity continues at current rates. The Baikal Rift Zone in Siberia presents another fascinating example of active continental rifting. Lake Baikal, the world's deepest and oldest freshwater lake, sits within an active rift valley that's been developing for approximately 25 million years. The rift continues to widen at rates of approximately 4 millimeters per year, with frequent seismic activity indicating ongoing crustal extension. While the Baikal Rift might not create new continental landmasses directly, it demonstrates how continental rifting can dramatically reshape existing terrain within relatively short geological timeframes. The Rift Valley has already created a depression over 1.6 kilometers deep, and continued activity could potentially lead to more dramatic topographic changes. The Rio Grande Rift in the southwestern United States shows how continental rifting can create significant new topographic features within human observable timescales. This rift system, active for approximately 35 million years, has created the distinctive basin and range topography that characterizes much of New Mexico and Colorado. While not creating new continental crust, the ongoing extensional deformation continues to modify the landscape at measurable rates. Perhaps most intriguingly, recent research has identified several locations where submarine volcanic activity might lead to the emergence of new islands within decades. The Colombo volcano northeast of Santorini, Greece, sits in relatively shallow water and shows signs of increasing activity. Similarly, several seamounts in the Azores region appear to be approaching depths where they might break the ocean surface during future eruptions. The Loihi Seamount, located southeast of Hawaii's Big Island, represents the most advanced example of a forming volcanic island. This underwater volcano has grown to within 975 meters of the ocean surface and shows frequent seismic activity, indicating ongoing magma intrusion. While Loihi won't emerge above sea level for several thousand years at current growth rates, a period of increased volcanic activity could potentially accelerate this timeline significantly. Satellite monitoring and underwater research have revealed numerous other submarine volcanoes showing signs of rapid growth. The Kavachi volcano in the Solomon Islands periodically breaks the ocean surface during eruptions, creating temporary islands that are subsequently eroded away. However, continued activity at this location could eventually create a permanent landmass. These modern examples demonstrate that significant new land formation is not only possible within human timescales, but is actively occurring at multiple locations around the globe. Having explored the mechanisms and locations of rapid geological change, we must now confront a fundamental question: what can realistically happen within a human lifetime? While the processes we've examined are indeed capable of creating new land at remarkable rates, the timeline for true continental formation requires careful scientific analysis to separate exciting possibilities from wishful thinking. The definition of continent itself presents the first challenge in assessing realistic timelines. Geologists use several criteria to distinguish continents from large islands: total area, geological composition, crustal thickness, and tectonic independence. By these standards, even large land masses like Greenland or Madagascar are considered islands rather than continents. Australia, the smallest recognized continent, covers approximately 7.7 million square kilometers, an area larger than the entire continental United States, Creating a landmass of truly continental proportions within a human lifetime would require unprecedented rates of geological activity. Even the most optimistic scenarios based on current hotspot and rifting processes fall far short of continental-scale formation. However, the creation of substantial new landmasses, potentially large enough to support significant populations and ecosystems, remains entirely possible. Iceland provides our best real-world benchmark for rapid land formation. The island currently covers approximately 103,000 square kilometers and has been growing for approximately 20 million years. This suggests an average growth rate of roughly 5 square kilometers per 1,000 years. However, Iceland's growth has not been uniform. Periods of intense activity have created much more rapid expansion than this average suggests. The most optimistic projections based on Iceland's recent activity suggest that under ideal conditions, a hotspot could create a new landmass covering several hundred square kilometers within a human lifetime. The formation of Surtsey Island demonstrates that even relatively small-scale volcanic activity can create permanent new land surprisingly quickly. If similar eruptions occurred in clusters around a particularly active hotspot, the cumulative effect could be substantial. The East African Rift presents different possibilities. The rifting process operates more slowly than hotspot volcanism in terms of land creation, but it affects vastly larger areas. Current spreading rates of 6 to 7 millimeters per year might seem insignificant, but they add up over time. More importantly, rifting events like the 2005 Dabahu fissure eruption demonstrate that significant changes can occur in sudden episodes. The most realistic scenario for witnessing dramatic geological change within our lifetime involves not the creation of entirely new continents, but the substantial modification of existing landmasses. The East African Rift could potentially create new inland seas or dramatically alter the shape of the African continent. Similarly, continued rifting in regions like the Baikal Rift Zone could create new topographic features large enough to affect regional geography and climate. Volcanic island formation presents the most promising avenue for witnessing significant new land creation. Based on historical examples and current monitoring data, several locations could potentially see the emergence of new islands within the next 50 to 100 years. The key factors include the depth of existing seamounts, the rate of current volcanic activity, and the geological setting. The Loihi Seamount off Hawaii represents perhaps the most predictable example of future island formation. While current growth rates suggest it won't reach the surface for several thousand years, increased volcanic activity could accelerate this timeline dramatically. Similar seamounts in other volcanic regions show comparable potential for emergence within extended human timescales. Climate change adds another variable to these calculations. Rising sea levels could submerge some newly formed low-lying areas, while changing weather patterns might affect erosion rates and volcanic activity. However, the primary drivers of geological change operate largely independently of surface climate conditions. The role of human observation and technology cannot be overlooked in assessing realistic timelines. Modern satellite monitoring, GPS, measurements and seismic networks allow us to detect and measure geological changes with unprecedented precision. Processes that might have gone unnoticed by previous generations are now carefully documented and quantified. This enhanced monitoring capability means that even relatively modest geological changes become significant from a human perspective. The gradual emergence of a new island, the expansion of existing landmasses, or the dramatic reshaping of coastlines through volcanic activity all represent observable continental formation processes, even if they don't create continent-sized results. The economic and social implications of new land formation also affect how we perceive the significance of geological timelines. A new island covering just a few hundred square kilometers could have enormous strategic and economic value, particularly if located in areas with significant maritime boundaries or resources. From this perspective, even modest new land formation could have continental-scale impacts on human affairs. Perhaps most importantly, witnessing any stage of continental formation provides invaluable scientific insights into the processes that shaped our planet throughout geological history. The formation of new volcanic islands, the rifting of existing continents, and the emergence of hotspot-driven landmasses all represent pieces of the larger puzzle of how Earth's surface evolves. The realistic timeline assessment suggests that, while we won't witness the birth of Australia-sized continents, we will likely see significant new land formation that advances our understanding of planetary processes and potentially affects human geography in meaningful ways. As we stand at the threshold of unprecedented technological capability for monitoring Earth's geological processes, the question of witnessing continental formation takes on new dimensions. While true continental-scale landmasses won't emerge, within human lifetimes, the processes that create continents are accelerating in several key locations, offering our species the extraordinary opportunity to observe planetary evolution in real time. The convergence of geological activity and human observation capability creates a unique moment in Earth's history. For the first time, intelligent observers can document, measure, and analyze continental formation processes as they occur. This represents not just scientific advancement, but a fundamental shift in how we understand our planet's dynamic nature. The East African Rift System will likely provide the most dramatic geological theater for human observation over the coming centuries. Current models suggest that within 10 to 20 million years, the rift will complete its evolution into a new ocean basin, effectively creating a new continent from the eastern portion of Africa. While this timeline extends far beyond human lifescales, the intermediate stages will produce observable changes within our lifetimes. The Afar Depression represents ground zero for this continental divorce. Here, the rifting process has advanced to the point where new oceanic crust is forming on dry land, a process typically hidden beneath kilometers of ocean water. GPS measurements show the rift widening at rates that will accumulate to tens of meters over the next few centuries, creating dramatic changes in regional topography. Volcanic activity associated with the rifting process offers more immediate opportunities for witnessing new land formation. The active volcanic systems throughout the East African Rift produce regular eruptions that modify local geography within years or decades. While individual events might create only modest changes, their cumulative effect over human timescales could be substantial. The Red Sea expansion presents another avenue for observing continental formation processes. As this young ocean basin continues to widen, it will likely produce new volcanic islands along its spreading center. Several existing islands in the Red Sea show rapid growth during active periods, and new islands could emerge from the spreading axis within decades. Iceland will continue serving as our premier laboratory for understanding rapid geological change. The island's position atop both a spreading ridge and a mantle hotspot ensures continued dramatic volcanic activity. Climate change adds another dimension to Iceland's evolution, as retreating glaciers reduce the weight pressing down on the crust, potentially triggering increased volcanic activity through isostatic rebound. Recent research suggests that Iceland's volcanic systems operate on cycles spanning decades to centuries. If current patterns hold, the island could experience a period of heightened activity within the next few decades, potentially adding substantial new land area through major eruptions. The 2021 Fagradalsfjall eruption offered a preview of this potential, creating new lava fields that added measurable area to the island. The Pacific Ocean presents numerous opportunities for witnessing new island formation. Beyond the well-studied Hawaiian hotspot, several other volcanic systems show potential for creating new landmasses within observable timescales. The Galapagos hotspot continues generating new volcanic activity, while the Azores hotspot in the Atlantic shows similar promise. Submarine monitoring has identified dozens of underwater volcanoes approaching depths where they might break the ocean surface during major eruptions. The Kavachi volcano in the Solomon Islands periodically creates temporary islands, while other seamounts throughout the Pacific show steady upward growth that could culminate in permanent emergence within decades. Technology will play a crucial role in how humans witness these geological processes. Satellite imagery now provides continuous monitoring of volcanic activity and land formation worldwide. GPS networks measure ground deformation with millimeter precision, while seismic arrays detect underground magma movement long before eruptions occur. Artificial intelligence and machine learning are revolutionizing geological prediction capabilities. By analyzing vast datasets of seismic activity, ground deformation, and chemical changes, computer models can increasingly predict when and where significant geological events might occur. This predictive capability transforms human observation from passive documentation to active anticipation of geological change. The implications extend beyond pure scientific interest. New land formation affects territorial boundaries, maritime rights, and resource access. The emergence of new islands or the dramatic modification of existing coastlines will require legal frameworks that currently don't exist. International law struggles to address situations where entirely new territory emerges from the ocean or where existing boundaries shift due to geological processes. Climate change adds urgency to documenting current geological processes. Rising sea levels will submerge some newly formed low-lying areas, while changing weather patterns might affect erosion rates and volcanic activity. The window for observing certain types of geological change might be narrowing, making current documentation efforts increasingly valuable. Perhaps most profoundly, witnessing continental formation processes connects us to the deep history of our planet. The mechanisms creating new land today are the same ones that built the continents we inhabit. By observing these processes in action, we gain insights into how Earth's surface evolved over billions of years and how it might continue changing in the future. The answer to our original question, could Earth grow a new continent in our lifetime, requires nuanced understanding. We won't see Australia-sized landmasses emerge, but we will witness the processes that create continents operating at scales and speeds that previous generations could never have imagined documenting. In that sense, we are indeed watching Earth grow new continental fragments, one volcanic eruption and one rift episode at a time.